Okay, now let's see how we're going to use these. And the thing that we're going to use these is something called isentropic efficiencies. Okay, we're going to be comparing real devices to ideal devices. Okay, how close are we to an ideal device? So let's look at our friend the turbine again. Okay, and we're going to deal with a very simple turbine. We have one flow coming in and one flow going out of this turbine. We're going to assume what we did earlier, steady state, KE and PE are going to be 0, and the heat transfer is going to be 0. And if we were to draw this on a TS diagram, the turbine, the steam coming into the turbine or the air coming in the turbine is going to start up here at state 1. And realistically, as we are producing some entropy, our state 2 should be out here. And I'll show you that here in a second through the equation. But we're looking at that ideal situation. It's going to go straight down here to the state 2, which we're going to say 2s. 2s, anytime we do an s on a state, we're indicating that it is isentropic. Okay? Here is going to be our state 2. And we'll put a dash line there because we're not exactly sure. So if we look at our equation, ds dt is equal to the summation of the heat transfer rate over the temperature plus the summation of my m dot n Sn minus the summation of my m dot xting Sxting plus sigma dot. And I do my substitutions. Delta S go to 0, or the steady state, sorry. There's no heat transfer. One inlet and one outlet. I get that 0 is equal to m dot times S1 minus S2 times, or plus sigma dot. Or that sigma dot is equal to m dot times S2 minus S1. So in a real turbine, you are going to have a positive number here. And to have a positive number, S2 has to be greater than S1. Look at that. That's what we're showing here. S2 is greater than S1. So that's why S2 always has to be to the right of S1. But if we have an ideal turbine, sigma dot is equal to 0, and S2 equals S1. Okay, so know that difference between a real and an ideal turbine. Law, our first law, okay, is equal to Q dot minus W dot plus the summation of my mass flow rate in enthalpy in minus the summation of mass flow rate xting times enthalpy xting. And notice I'm not taking into consideration kinetic or potential energy terms. I'm just eliminating them. I'm simplifying my equation. Okay. If I go through my substitutions here, or my assumptions here, your energy is going to go to 0. You're going to have no heat transfer here. And we're going to say that W dot of my turbine is going to be equal to m dot times H1 minus H2. Okay, that corresponds to this state 2 up here that we have still. It's corresponding to this state 2. Okay. Now, this is going to be our real turbine. An ideal turbine is going to say W dot turbine, and I'm going to put TS, so I know it's ideal, is equal to m dot times H1 minus H2S. This is going to be our ideal turbine. What we're going to find is that H2S is going to be a lower number than our H2, and that's where more energy, more power is going to be produced from that turbine. Okay, 2S corresponds to the S2S state above. Okay, that's how they work. That's how they can connect. So what I want to do is I want to find out what an isentropic efficiency is. An efficiency is a number between 0 and 1, or 0 and 100%. And so, if I look at my isentropic efficiency of my turbine over the ideal, and I put the actual over the ideal because my actual power is going to be less than my ideal power, and I'm going to have a number between 0 and 100, 0 and 1, 0 and 100%, 0 and 1 in decimal values. Okay, so what is our actual work? It's going to be m dot times h1 minus h2. What is my ideal work? It's going to be m dot times h1 minus h2s. H1's the same in both of these because the steam coming in or the air coming in does not know what kind of turbine it's coming into, so it's H1. But as it comes out, it's going to be different depending on how that turbine effectively used the energy. Okay, my mass flow rate is going to be the same, so these are going to cross out. And we're left with that the isentropic efficiency of a turbine is equal to H1 minus H2 all over H1 minus H2S. If we were dealing with ideal gases with constant specific heats, so ideal gases and constant specific heats, what will we find there? Well, we could say the isentropic efficiency of a turbine is equal to C sub P times T1 minus T2 all over C sub P times T1 minus T2S. And of course, my C sub P's are going to cancel, and I can just say that the isentropic efficiency is equal to T1 minus T2 all over T1 minus T2S. And we're going to use all the equations that we had in the previous lecture segment to help us find out what T2S is or what H2S is by finding state 2 or S2S. Okay, that's what we're going to try to find, and I'll show you in some example problems how we're going to do that. Okay. The other thing I'm going to show you is how we're going to do with a compressor or a pump. A compressor or a pump. So, let's look at a compressor or a pump. Okay, we know the compressor does gases, a pump does liquids. Okay, so again, we're going to be drawing, I'll just do this for a compressor, same equation for a pump. So, I'll look at it this way. We're going to be putting in some power here. And again here on a TS diagram, we're going to have two lines. Here's going to be a pressure 1 and a pressure 2. And we're going to come in here at state 1. And we're going to go up here to state 2S. And ideally, that's where we would be. But actually, we're at state 2. Okay, we're going to be 2B right. Just for all the same reasons why we were for a turbine. I'm not going to repeat those. Okay. So let's look at what this is going to be. This is our first law. It's going to be dE dt W dot plus the summation of my mass flow rates N times my enthalpy N minus the summation of my mass flow rates Xting times my enthalpy Xting. We're making all those same assumptions. Steady state, adiabatic, no kinetic or potential energy effects. And we're going to get the same equation here, that W dot of our compressor is equal to M dot times H1 minus H2. Now here's the thing with the equations I'm going to show you. What is this W dot going to give us? It's going to give us a negative number. We know that the power is required for a compressor, so this is going to give us a negative number, H1 minus H2. But at this point in time, I hope that you know that a compressor gives a negative, work is needed, so it's going to be a negative number. So what we do in this study is we say, all right, I don't want to deal with the negatives, so I say that the work of a compressor, I really work with the absolute value of this. So look at the real, is going to be M dot times H2 minus H1. And whatever I calculate there, I say, I know that's the magnitude of the compressor work, and I'll just say, I'll assume a negative sign on that in my head, or it's going into my system. And then my compressor, when it's ideal, is going to be M dot times H2S minus H1. And now our question is, which one of these is going to require more power? Our real or our ideal? Which one is going to require more power? Well, that should be, it's going to be the real one is going to require more power. And so when we do with our isentropic efficiency of our compressor, it's going to be actually ideal over real, because again, we want the thing that is bigger in the denominator, so we have a number between 0 and 1, or 0 and 100%. So this flips them from what we had for a turbine. So this is going to be equal to m dot times h2s minus h1 all over m dot times h2 minus h1. And again, my mass flow rates can cancel, and I get the isentropic efficiency of a compressor is equal to h2s minus h1 all over h2 minus h1. This will be the same equation for a pump. h2s minus h1 over h2 minus h1. This is going to be the same. So same for a pump. Okay. And what happens if we have an ideal gas with constant specific heat? We're going to say the isentropic efficiency is equal to C sub P times T2S minus T1 all over C sub P T2 minus T1. And my C sub P's are going to cancel again. And I'm just left with T2S minus T1 all over T2 minus T1. This is again the same for a pump. Now we can also do these for a nozzle, and you can do that for a nozzle. I'm not going to show you for a nozzle. I will tell you for a compressor and for a turbine, you're going to be efficiency like 85 to 90%, somewhere in there. We're going to study our problems in our class are going to be specifically on talking about compressors and turbines, what we're going to be working on. If you can understand those, I think that if I then gave you the equation for a nozzle, you'd be very comfortable with, and you will need that in Thermo too as you're dealing with jet engines and things of that nature. But in the time that we have and the amount of lectures we have, I'm going to only concentrate on turbines and compressors here, and then I think you can add that other material in as you get going. So we'll stop here for this, and then we'll work on some problems next.